Alright, so over in Python here, first let's import some things that we're going to find useful. Yeah, what is it? Hold on. Algebra. Okay. I think that's good for now. So, of course, I'm going to be using NumPy, and this solve banded here. This is going to be useful for when we're dealing with our, I guess, if you want to refer to that as our A matrix, our coefficients, right? Where there's basically those diagonals with our different coefficients, and those diagonals. We'll have three diagonals. And those are basically going to be surrounded by zeros. So this is basically going to be a tool to handle that. And I know that there's, I did end up overlaying that image, but I'll get to that when I feel, it'll be appropriate there. I don't want to explain it and then not talk about it for 10 minutes. So. Moving forward here, how do we want to start off approaching this problem? Well, I guess similarly to what I did on paper, let's go ahead and work with the constraints of our problem. So remember, we had some differential x's and differential t's that we were working with, our discretizations. So let's go ahead and say we have actually, let's start with the numbers first, right? Because if we have a 50 meter bar and our discretizations are 1 meter, right? We're going to have 50 of those, and maybe actually even better would be like a number of delta x. All right, and let's do a similar thing for our time. Right, we had 3600. Okay, and then we'll have an alpha. Do we want to call it alpha? Yeah, that'll be fine. That's 1. Oops, I don't want that. I just want 1. And then we're going to have our actual delta x, and that's going to be 1 as well. And then our tx, that's also going to be 1. So now we kind of got the bare minimum of what we need. Okay, so maybe now's a good time to talk about our little, image I overlaid. So, of course, we're going to need to create an array for our temperatures, right? And as stated, I know, I guess you can't see my mouse when I'm pointing over at the image, but that darker orange 0 in our T array, right? That's our left bound where the temperature is remaining at 50 degrees Celsius. And then, in that lighter orange on the far right boundary, that's also that unique case we have to keep in mind where there's, some perfect insulation going on there, right? Where that 49 is perfectly insulated. So, to do that, let's create a range for our, let's create a temperature array. Right, so let's actually let's just, because all the values, let me double check real quick if they're 20. Okay, so I double checked that, and it looks like the initial for most of the bar is 20. So let's do this should be the entire length of our discretizations, and let's fill that with 20. And then we want the temperature, right, that left bound, right, we want that to be 50. Let's print that and see if that looks okay. Okay, so now we have, this is essentially, looking over at our image again, that's our T array, right? So we're starting off, initially at our time 0, this is just initial. We have our 50 as our left bound, and everything else is 20. The other thing we probably, I'm just thinking, because at some point we're going to want to graph these these like this, these kind of iterations that we're going to be running through, solving for these different temperatures at succeeding times, right? So we're going to be making multiple plots. So we're going to want to be, at some point we're going to be wanting to plot the temperature with respect to a certain position. So another thing we probably should do is create a, like our x values, right? So let's create a, how should I do this? If we're increasing, we probably want a range. And what is that one? It wants a start and a stop. So we probably want to do, well, if I do my number of delta x's, what does that give me? Right, that gives me all of these, but I want to multiply those. Actually, yeah, that should be fine since, in our case, our delta x is 1, so that won't make a difference. But just for, I guess, robustness sake, let's stick with that. And then, okay, so if I'm looking at my image again, I'm going to need, okay, do I have everything I need before I start moving on to like my A, X, and B kind of matrices? Well, I'm going to need to define R, right, because we're going to be using that in our coefficients. So R is going to be equal to, right, that's going to be alpha times our delta t, right? Our delta t here is, oh, I don't like that. I made that tx. That needs to be dt. So let's do alpha times dt over 2 over our delta x squared. Why is that underlined? That's weird. I have no idea why that's happening. Is that okay? So R is 0.5. So if we have 1 times 1 divided by 2 is 1/2. Divided by 1 squared. Okay, yep, that's correct. Okay, so now that's all good now. We can move on to our arrays then, I guess. So let's just kind of work left to right. I know you kind of can't see what I'm seeing, but if you remember what we were working through on paper when I kind of wrote out a rough framework for our matrices, right? Let's first off, I think as opposed to using full, right? Looking at on my paper here, these diagonals are surrounded by a large number of arrays. Actually, thinking about this, I don't want my actual A array to include. So okay, so let me let me backpedal here. We're going to be using this solve bandit at some point, right? And for example, this solve bandit, the parameters for this, it asks for the number of diagonals below and above the main diagonal, right? So if I'm looking at this this kind of literature here, this main diagonal here, it's asking for what's above and below that, how many diagonals there are that aren't filled with zeros, right? Actual information. And it asks for an AB matrix and a B matrix. And this AB, in terms of my explanation earlier on by hand, that would be our A array, our coefficients array, right? And the way this asks for AB, right, it just wants the diagonals, essentially, if you imagine those diagonals, imagine just, creating an array with those diagonals, but those diagonals now run horizontally, right? And in order to, maintain a valid shape, right, any points if the length of any of those diagonals is less than the main diagonal, you fill those extra points with zeros, right? So in that case, we don't want to make A be a full array of zeros. That's the entire span. Instead, we want zeros. If we think about the number of diagonals we have, we'll only have 3 diagonals, because essentially for most things, we'll have a negative r as our lower diagonal, and then our main diagonal will be some form of 1 plus 2r, and then of course for the right boundary all the way at the bottom there should be a 1 plus r, and then above that diagonal we'll have a a diagonal of negative r's as well. So that means we're going to want a 3 by right, because we want this to be correlated, right? Because this a is for these are the coefficients that are being multiplied by our x array, which is what's unknown, right? So if we look over at our our temperature array, the only thing we don't know, or in fact the better way to say it would be the only thing we do know for certain is that 0 indice, right? That's always going to be 50 degrees. So everything after that will be unknown. So in that case, let's say that's ndx minus 1, right? Let's check that. 49, right? Because okay, that looks good. Okay, so now let's work on filling this up, because right now it's just zeros. So if I think about my diagonal above the main diagonal, that would be at so let's go top down, right? Because that's how Solve Banded likes this to be inputted as, right? So our so then we'll say because we have 3 rows here. So let's say in our first row, or 0 row, we're going to want a negative r, but remember for where j equals 0, right? We don't have anything to the left of that. The way our matrices worked out, we only had a 1 plus 2r and then a negative r, right? There was no negative r beforehand. Okay, so then that would be 1, and we'll want everything else, and that'll be equal to negative r. Let's print A. Right, okay, that looks good. And now let's do our 1 plus 2r, right? This is where we're at the diagonal. All these associated coefficients are with the actual j value that we're solving for, not j plus 1 or j minus 1, right? So in that case, right, we're going to be, this is our next row, and why don't we just let's make everything right now. Let's see. It looks like it's 1 plus 2 times r. Right, we call this r, okay. And then let's not forget, all the way at the bottom where our boundary is 1 plus r. That would be right in the same row, but we want the that associated indice, that'd be 48, and we want that to be 1 plus r. Okay, so that's our a value for j. Now let's do our next thing here. So now we're going to need right, we're going to be at a new row, and this time we're going to want to well, this time, right, this negative r at j equals 0 is still being used. So this time we actually want to start at the beginning, and then kind of in an opposite way. This time, all the way at the end, where we're at the right boundary, right, we only have a negative r, then a 1 plus r, and then our j plus 1 is actually a 0 value, right? So this time we actually only want to go and exclude that last point. And that's also a negative r. And right, and then of course we want to take that 2, and then at that same position, right, we want that to be a 0, right? Because right. We want that to be a 0, right? Okay, so let's take a peek right here and see how this looks. Right, so we have our 0 there, and we have our 0 there. Okay, that looks right. And then of course, I'm assuming this is what 1 plus r is. This is what that difference is. All of these are 1 plus 2 times r. So I think for right now that looks to be correct. That looks to be correct to me. And I'll just do this just in case we have to come back and troubleshoot this. J plus 1. Okay. So that looks okay to me now. The next thing we probably want to do is our X array. I mean that's what we're gonna be solving for with our solved banded actually. So I don't even want to do that right. Yeah, that doesn't even make sense to be doing. So I want to move on to B. My B. So similarly, this is going to be pretty much the same thing, except this is going to be one-dimensional, right? Because if you remember, not to get confused that, there were multiple terms and it might have looked like there were multiple columns within that B array, but, right, AX equals B, right? This is, the same dimension as our X array, right? Because those are all known. All those things we're adding together were known. So, not to get confused by that, we just want a one-dimensional array, and of course this is going to be nx. No, we used number of, dx's. So we want that. So just to double check this, make sure we're on track. Oh, that's not right. No, this has to be -1. Right, b dot shape, and then let's test our a shape just to make sure we're on the right track. 49. Okay, that looks good. So now we have to handle our b values now. So let's do that. First off, I just want to think about handling the general case, right, where we're not at the boundaries. So I'm going to print b, and let's use this visual representation I have, up here, right? Because I know, again, you can't see my mouse or my pointer, but if you look, there's a slightly shaded, there's a slightly like a gray vertical bar around the two boundaries, and those are key points because looking at those, when you're looking at the 0th position of the B array that we just created, that B array, or that associated temperature, that position on the T array, is that's going to be unique because its J-1 is actually using that consistent known value that's 50 degrees Celsius, right? And we handled that and took care of that. So we're not interested in that right now for the the general case, for all those purple intermediate values. So and similarly at the end, right, we're not going to want to include our 48th position in the B array, 48th indice, because at that point, right, that's where our right boundary is, and while that doesn't remain at a constant temperature, it is considered to be unique, right, because we have that perfect insulation. So we are going to just want to, for this general case, we're only going to want to make changes to, okay, so if you're looking at the purple, that purple section, that's what we're going to want, right? That's 1 to 47. So I believe that should be, we're going to want to change the B values from position 1 to -1. All right, so let's do 1 and -1. and that should be equal to R times the temperature. And so I also, in that image, I have a handy, you can see at the temperature array, I made this ahead of time. You can see how I'm referring to the positions, right? Because if you're looking at the J values, where the orange bracket is, right? Those are all the cases that don't, that calculation with the temperature at J minus 1, J, and J plus 1, right? Those values will not be, I won't have to worry about like a unique condition, right? So, if I'm doing like left to right, the way I'm doing these B values, let's say this term I'm typing right now is our J minus 1, right? So we want to, in that case, if you're looking at our diagram, we want to include 1. Oh, sorry. Oh, no, yeah, that's right. Include 1, right? And we want to exclude 48 because that utilizes, right, because we're shifted to the left. So we want to do 1 minus 2. And then we want to add our 1, right, our 1 minus 2 times R, and this will be multiplied by a temperature. This will be our, our actual J that we're interested in, right? So that'll be from 2 to 48, right? That's kind of the key here, right? So it's going to be 2 to negative 1, right? And then since that's our J, J plus 1 will be shifted 1 to the right. So in that case, our J plus 1, let me look again here, that's a positive R, right? So positive R times temperature, and this time it's going to be from 3 to everything. It's going to include everything, right? I think that's correct, and I'm going to print this just to see how that looks. Right, because I changed all, yeah, right, because we're not iterating anything right now. This is just our initial, this is at time 0, right? So now we need to handle our boundary condition here. So let's think about that. So looking back, what I have on my written paper here that you can't see anymore, unfortunately, our B value. Well, our B value, right, for at our left boundary, which is at position 0, that's going to equal, right, at this previous point, we calculated the, the general, our general B value for everything. And then, we found that at the left boundary, we're also going to have to add on to that general form the temperature to the left of our J, which, if we're at J is 0 to the negative 1 is also going to be, well, really our temperature is 0. So now we're going to have, our original calculation there, and then plus R times T at that same position. So let's print that again. Okay. Right, so now it's 20 plus R, so 1/2 times, that's going to be, right, because at this position actually it was 0, remember? Before that change we had a 0 at both the boundaries, right? So that's plus 1/2 times 50, which is 25, and that is correct. So now let's also consider our right boundary. So similarly, pretty much exactly the same as we did for this B value. We already figured that out by hand. So that's going to be our B at 48. And that's going to be basically what we solved for at that unique case. So it's going to be R times our temperature at, right, our J minus 1 is, for at 48 minus 1. 48 minus 1 plus R, is it 1 plus R or 1 plus? 1 minus r for this. Yeah, right, because it's the b side. 1 minus r times the temperature at that position at 48. Okay. Yeah. And that's correct. That should be correct initially. So the next step to take here is doing this, because we could solve banded and solve our n+1 right now, and maybe that's what we want to test. Let's see what we're getting here. All right, because our unknown, right? Our unknown start at the first position and continue all the way to the right boundary. And let's do our solve banded. And in our case, we have one above and one below the diagonal, right? So we have that, and then our AB is A, and then we have B. Yes. Okay, let's see what T looks like. Okay. Maybe let's think about a plot here. So let's make call it fig, and we'll do. Oh yeah, I don't think I imported any of this. Okay, 1 sec. I'm gonna have to double check the syntax for this. Okay, so I went ahead and put these in. I don't know these off the top of my head, so I didn't want to stumble through that. But yeah, so we're going to, this is just some basic plotting stuff. So again, we're going back here. We're going to say fig, and we're going to use this time. We're going to use our make subplots, right? So let's make subplots. What do we need to give it? We need rows, right? I need to give it dimensions. So we'll do rows equal 1. Is it calls? It's not really popping up. I think it's calls. And then to our fig, right? Let's do a scatter. Is it add dot or add scatter? Oh, I bet that's why it's not showing up. I have to run this. Okay, let's go back. Fig.add. Actually, let me run this first. I need to define fig, and then we'll go fig.add. There we go. That's what I want. Scatter. Clip on axis. Right, this is why we made, the X originally up there, because we needed to, right here, because we have to plot, right, and that's our y-axis, and name. How does that work? What's that? Name. Name. So that's the trace name. Okay, so let's just call that initial. Yeah, we'll just do that for now. Let's see what happens. Right. Okay. That's 17. Why is that 17? That's 1. Let me plot T real quick. I want to see what's going on there. Why the heck is that 17? Yeah, that's probably weird because that's yeah, I think that's because that's only my first. I don't know though. That doesn't seem right to me. I'm gonna take a break here and check this out. I think because I really don't have any idea why that's happening. Okay, so I think I recognize what it was. Pretty obvious looking back. B of 0 right now. I didn't I didn't perform the general thing. When I actually wrote that, I was like, oh yeah, it was right here, but I actually didn't do that. Right. So let's go ahead and do that before the kind of general kind of thing, and it'll be pretty similar, but will be very similar, right? Because then we'll have basically that, and then we'll have our 1 minus 2 times r times t at 1 plus right, and if remember the indices are kind of off by 1, right? Because our b is one size smaller. Not to get confused that because this is our j, but this j is 1 off of what b is, right? So don't get hung up on it, right? So then this one's t and then 2. Why is it not showing my... There we go. Okay, that's what we want. So that was the mistake there. So this is, essentially what I plotted here. This is my temperature at n+1. So what we want to go off and do now is, perform this iteratively. So how do I want to do this? I think I'm actually just going to comment these out because I'm going to use them in some sort of loop. But I don't want to get rid of it right now. So let's make a loop. So for I think it's I in range, start, stop. So right, we want to go 1, and then our number of x is +1. Oops, get a colon in there. Okay. No, we don't want to do that. This should be our time. Right, because we're going to be plotting, let's decide that, when we're plotting, we're going to want to do it every 5 minutes. We want to plot every 5 minutes. Okay, so we're going into our loop now. What is going to be changing inside of our loop here? A and B, so we have an A and a B. Okay, let's just think about what's going to be changing. Initially when we defined these, this cluster right here, those are all constants. We're initializing our temperature array here initially, but that is definitely going to be changing, of course. That's exactly what we're, that's the crux of what we're plotting. X will not change. R is a constant. Will A change? A is made up of coefficients which solely contain some form of R, right? And R, as I just said, that's a constant. So okay, so we don't have to worry about A either in that case. So right now we only have the temperature that's going to have to be included in some form in our loop here. And if we're looking at our B, right, that's going to be a collection of our coefficients and our temperatures at the previous time n, right? Because when we start off, we'll find our n+1, and then that's going to become the temperature at n, and we're going to be solving for the succeeding time, right? So that's also going to be changing, right? So let's I guess first off, let's take our B. We still want to initialize it outside, but let's go ahead and carry our B's into our loop here. Let's fix the spacing. Okay, so now we have our B's in here, and we're also going to need our temperature to change. Our temperature, so we're basically going through and our B's are changing, right? Those are our known values. So we have our known B's, that's being taken care of here, and we have our coefficients which don't change, and we're solving for our temperatures at +1, which is essentially what this is doing right here. So let's throw that in there. And okay, so this is going to solve for our temperature n+1 each iteration, right? So then, right, if we said we wanted to plot every 5 minutes now, we don't want to be plotting every single iteration, right? Because this d and t, this is in terms of seconds, right? That's d and t. That's not right. This should be our total. Yeah, because we want to iterate through this all of our time. That's nt. Yeah, ntx. That was a good catch. Okay, so ntx. Right, but we don't want to plot every single one of those, or we'll have like thousands of plots, like lines on our graph. We don't want that. So I forget the word. I'm gonna have to take a break in here and check this out. It's basically, I think it's something like how to test the remainder, like how divisible something is. So give me one sec. Okay. It's referred to as modulus, right? So we're gonna say our iterative kind of index, like I guess our counting variable kind of, maybe that's the way to say it, modulus, and right, if we want to do it every 5 minutes, that's going to be 5 times 60 seconds, right? So then that's going to be 300, right? And we want the remainder of that, of this, this modulus thing to be 0, right? We want it to be exactly every single 5 minutes. So every single time, now we're going to want to add the plot on our we're going to want to add another scatter, right? Because we have that up, right here, but we're going to want to add a scatter for each of these iterations. So now let's do another add scatter. Oops, it's got to be a dot. What am I doing? That's got to be parentheses. And this time, right, we'll say x equals x, y equals t, and what is it? Like mode. What is mode? I think that's what it is. Mode. Lines. I want it to be lines. Okay. I'm not 100% sure if that's going to work. I think that's the right idea. Okay, and then let's show. Please work? No. ntx is not defined. n_tx. I can't even remember my own variable. What is that? n_tx, the number of time slice. Okay. Maybe I should have just kept it as tx. That's okay. So ntx. Okay. Please work. Okay, it didn't graph. Fig.show. Why didn't that work? What did it? I don't know why it didn't work last time. Okay. This looks pretty good. All right, so okay, so our initial is here. We can name these. So what did we call it? We said name equals initial. So this time, let's say name equals, how should we do this? This is, oh, I think I know. Okay, so let's do integer. And let's do I divided by 60, right? So let's get into the correct unit here. And then, oh, I need parentheses around that, I believe. No. Right, because it's into, okay, no, yeah, I need that here, parentheses, parentheses. So that should be good now. That still doesn't look right to me. I would put the parentheses in the wrong place. Okay, now I believe that's correct. And, right, and with that unit, that will be minutes. Maybe I don't need that. Maybe I can just type it. Okay, cool. So let's see if that works. Nice. Okay. So look at that. Right, so at our initial, right, this is when our node at position 0 is 50, everything else is 20. And as you would expect, the temperature, the gradient, for each of these slices going, as the time increases, it obviously will become more linear, right? But, initially the temperature gradient, the temperature will be higher the closer you are to that left boundary, right? Because that boundary is always 50 degrees Celsius while everything was initially 20, right? So, you have it slowly evening it out each time. And I believe that when you see this, this flattening out here between 49 and 48 should be exactly the same, because that's let's see, 5654. Okay, no, sorry, that shouldn't be exactly the same, right? We didn't plot the insulation, obviously. This is the temperature bar, but yeah, that's it should just smooth out as you get closer to the insulation, I believe. So maybe another thing we want to do here is I think we can maybe change the our x-axis to be a little bit more well, I think that's good. I think that looks pretty good to me. So I think this kind of is a good demonstration for how useful Crank-Nicolson is for diffusion problems. Particularly often because those are like when you end up doing the numerical calculations from that partial derivative, you can run into problems with that R, but that Crank-Nicolson method really irons things out, and me going through this myself, I can see how I can see why really it's so widely used. So I hope that was informative. Thanks for watching.